Hi, I'm Bill Kennedy with Arden Labs. I'm the managing director at Arden Labs, but primarily I spend a lot of time training companies in Go. And in our talk today, we're going to focus on the Go tracing tool and get an opportunity to look at a running program, see what's happening with that program using tracing, and maybe potentially find some ways to improve its performance. So let's get started. We have a lot to get to. So here's the program that we're going to be focusing on. We can imagine that it's potentially a CLI tool, and what this tool does is it tries to identify the frequency that a given topic is found in a set of news feeds. Now here's one news feed that we'll be working with. You can see it's an XML-based document. We're actually going to pretend that this one document is about 4,000 for the work that we will do here today, but you can see what we're going to be trying to consume. Let's walk through this function first to get a general sense of how it works. And so we pass in that topic and a collection of documents. And you can see there in line 54, we declare a variable named found to help add the frequency that that particular topic is found in. Then we use a go for range loop to iterate over that collection of documents. There could be one, there could be a million. We don't really know. We have to consider that at some point in the design of the algorithm. And then, really to keep it as simple as possible, I've broken up the 4 steps that we need in order to process every given document. So the first thing we've got to do is open it. Then we're going to read the entire document into memory. It is an XML document. We can't really kind of process it as a stream, in chunks. We need the whole thing. Then we're going to marshal that XML into a Go value that will allow us to then see the items for each title and description, and anytime the topic matches, we increment the found variable. So we've got these 4 stages here. Now what you're also seeing is a single-threaded, a single Go routine-based algorithm. I always want to try to keep things simple until I can't, and concurrency is really, really hard code to write, even in Go. Go, you may have heard people say, well, no, it's so much easier to write concurrent code in Go. It might be less complex than other languages, but it's still super complex, right? And for our purposes, the word concurrency means out of order execution, right? So writing something there where the order of execution doesn't matter. Now, this is a single-threaded function here. It's just going to do that iteration. It's going to walk through everything. And so we've got a version now of this algorithm. Now, a couple things here. Here's our main function, okay? And what I'm going to do is take that newsfeed document that I showed you and pretend that it's 4,000 unique documents. I'm going to create some fake names here, kind of in that loop on line 44 where we set it all up. That's why you see us kind of parsing the fake name out here on line 57. The topic's going to be president, and then we're going to call our frequency function, and then we will output to standard error. The log by default will write to standard error what the number of documents we processed and how many times that particular topic, in this case the word president, was found. Okay, so we've got our program here. I'm going to go over to our terminal window, and what I'm going to do is run go build. Go build will give us a binary of that trace program, and then what I can do is I'll use time here in the terminal just to give us a basic wall clock on how long it's running. Then we can run our trace program, and if I just do that right now, and I'm going to run everything twice, right? Get that machine warmed up, and then we'll run it again. I feel like it's maybe a little bit more accurate when I run it the second time. And we can see here the second time I ran it, we processed those 4,000 files, found the term president, a topic, 28,000 times, and the program ran for about 1.5 seconds. Okay, we've got a good benchmark now to kind of start moving forward. Now here's the reality. If we were only ever going to be processing 4,000 files, I would say that this program is fast enough and we don't need to add any more complexity to make it faster. But I had told you already, I kind of want to be able to process 1,000,000 files, at least at some point. And I feel like processing 4,000 at 1.5 seconds isn't really reasonably fast enough, and if there's a way to make it faster, we should. And this is what we're going to try to do now. But again, anytime that you're going to be trying to make a program run faster, there's a good chance that you're going to have to be clever, and it's going to be this trade-off between complexity of the code and that performance. There's always a trade-off. Nothing is free. There's always something that there's a cost to. Okay, so how can we start to begin to try to find a way to make this program run faster? Now, Go has a couple of tools here. Go has profiling tools. We could take a memory profile or a CPU profile of this program. We don't have a lot of time to do that today, so let me just say this about profiles. I love profiles, and I can absolutely teach you how to use a profile to help identify performance issues in your Go code. However, a profile is limited in this one way. It can only show you what is happening in your code. It can't show you what's not happening. Now, I'm not saying the problem that we have is based necessarily on what's not happening, but if you want to see what's not happening in your program, Go gives you another tool, which is the tracing tool. And that's the tool I want to use with you today, the tracing tool. The tracing tool essentially does trace your entire program and allows you to see a tremendous amount of information about that running program. Now, the trace tool gathers a large amount of information, so we really don't want to try to take traces, at least I try not to take traces that are more than a few seconds long because the information is pretty big. But this program only runs, at least right now, for 1.5 seconds, so it's not a problem. Now, there's lots of different ways to get a trace of your Go program. Today in this talk, I'm going to show you how to use the standard library and access that trace package. That trace package comes out of the runtime. And so with the trace package, what we can say is write that trace to standard out, defer it, stop, so it flushes, and I can just redirect the trace information to a file, and then we can use the trace tool to start to inspect the program. Okay, so I've saved this now in here. Let's go back to our terminal. Let's build this again, and this time when I run it, I'm going to redirect that standard out to t.out. And like I said to you before, I'm going to run it twice every single time. Okay, now I'm not surprised that it's running a little slower because we're gathering all of this information, so that's okay, but it's still reasonably about the same. We went from 1.5 to 1.6 here on our wall clock with time. But now what happens here is we've got that t.out file. Notice how we've got a 1.4 meg file, even only running for about a second and a half. Okay, how do we start to inspect this file? Well, go tool trace t.out. There it is. And what that will do is now bring up the browser. Now, if you're running in 1.19, you're going to get all of this goodness now, documentation about all the different options you have in reviewing this trace. If you're in 1.18 or less, then you're just going to kind of see the links, and the documentation is well, really, there isn't any. It's just really just going to be links. But this is one of the changes they made in 1.19, so it's very, very cool. Now, for our purposes here, we're going to view this trace. So let me click on that link. I'm going to hide this message. There was some Chrome bugs several years ago that broke some of the components. It's just a message to let you know at this point we don't need it. Okay, so this is pretty cool. This is our trace. Now, I know that the colors are a little pastel. I think the person that colored this stuff doesn't give talks. I do wish that these colors were a little darker, but we'll handle that. It's going to be okay. Now, We can see here on the left that we've got a whole set of information, Go routines, and this really goes down to the microsecond here, the microsecond. So like down to the microsecond, how many Go routines this program had at any given time, the heap profile, which we're going to be looking at, the number of operating system threads, and then we're going to be looking at the different logical processors that Go uses to execute Go routines. That's what you see down here, right below the GC information. Now, I want to start to kind of gather a little bit of information. We're going to write that on the whiteboard behind me as we go. One of the very first pieces of information that I want to look at is like what the trace says this program took to run. And we can see here that it was 1.6 or 1669 milliseconds here. So you don't see this yet on the board. I'm just going to start writing and then I'll show you, I promise. But the total runtime, right, of our program is 1669 milliseconds. We'll do everything in milliseconds here. Okay, so we've got that information here. Let me clear that. Let's take a better look at this trace. So the Go tool allows me to kind of expand the timeline a bit. That's what I'm doing here. I'm going to use this that tool here to expand a little bit more and move it. And we can start to kind of see a little bit of what's happening within that first, I don't know what that is, 60 milliseconds or so, 60 milliseconds of information. Now, what I want to kind of focus on is a couple things here. I want to kind of explain what's happening here in the heap graph, and then we'll work down. So there's two colors here that you see. We see that green line, and then we see these orange lines that are popping up and kind of coming back down. And if you really notice, when one of these orange lines sort of drop, we get that edge, there's a blue line just underneath it in that GC column. So those blue lines that you see in the GC column are garbage collections that are taking place. And we can see that orange line is dropping. So what do these two colors mean? Okay, so the orange line is showing the amount of memory that is in use at that moment in time. And that's why you see that increasing. Because think about what this program is doing, right? It opens up a file, that takes some memory. It reads that entire file in memory, that takes up more. Then we have to unmarshal that, that's more memory. Then we read through that memory, and then we're done with it and we let it go. So the memory that's being used by this program is very transient, isn't it? And so we see essentially a bunch of files being processed, and then at some point a garbage collection occurs. Now, I just kind of clicked in this area right here. I can even maybe just click out a little bit. I'm trying to get right at the edge there. And what I'm looking for here is this allocated. I want you to notice that what's happened here is that the program is allocated 4 meg of memory at this point. And then that garbage collection started. And when we don't play with any of the settings in a Go program, that's when that first garbage collection will take place, 4 meg. So this is very, very normal. We allocated 4 meg of memory. The GC started. It was able to bring that memory down. And then we ran again. And if we come here, if I can click in the right spot, there it is, 4 meg of memory allocated again. Now, the green line here, this green line that we see here, all right, and excuse me for the values, but what this green line represents is really the next GC. When should the next GC start? And ideally, what's happening here is that green line is holding fast at that 4 meg. So this program, the garbage collector in this program, is essentially able to start a garbage collection now every time the heap allocates up to 4 meg of memory in use. And this is a very consistent graph. So the garbage collection is, in a sense, doing its job to keep the memory, right? The amount of memory being allocated by this program, consistent and small. It's able to keep a 4 meg heap throughout the running of this program. That's another thing I'm going to write on the board that you're going to see so far, really. Like the max amount of memory we've had to allocate in this program, it's been pretty consistent at 4 meg. That's the garbage collector trying to, again, focus on that resource usage. Why? Because your programs are going to be running in the cloud, right? Ideally, they run in the cloud. They run in containers. And so being able to keep that low memory limit is pretty important, right? Especially with the way we run software today. And so here is the Go program saying, you know what? I can keep the memory of this Go program at or below 4 meg. I'm going to do that. Okay, brilliant. So we've learned a little bit. Orange is in use, it grows, it reaches basically what the next garbage collection is going to take in terms of in-use memory. We're seeing that that's at 4 meg, and boom, a GC takes place. Now, I could expand real quick one of these garbage collections, but I need you to understand that it's never about one GC. It's really about GC as a collection of multiple garbage collections. But here's a GC that happened, right? Here's the Go routine that's running our software. You can see it went into a mark assist. It's starting to help the garbage collection do some GC work. We can see that some of these logical processors are dedicated to garbage collection as well. We do see that we are concurrent with the GC. Around this time, we are doing application work while the GC is running. And then at the end of the GC, we have this mark termination phase here at the end. So, and the sweeping of memory happens outside of the GC. The GC process is really about marking memory that is and is not in use. Okay, so we've seen that. But you know what? We're here today to really try to figure out how we can leverage this tool to help find potential performance issues that we can fix. And I kind of like this view right now because it really clearly, I think, gives us an indication of why we're not as fast as we otherwise could be. This view is making it clear that, one, we are a single-threaded Go program. The only Go routine we have, G1, that's our G1, the Go routines are numbered as they're created, with the main Go routine, right, the one we're using is G1. We can see that it's bouncing between these two logical processors, but that's it. We are a single-threaded Go program. The machine that I'm running on right now for this program is an M1 with 10 cores. And if you notice that we're not even using all 10 cores, I only have 6 of the 10 cores in use. We can think of these logical processors as bound to a core. So I should see 10 of these. I only see 6 of these, and we're not even using it. The garbage collector during garbage collection is using more of our CPU capacity than we are. So if we want to speed this Go program up, it's not really right now about anything other than leveraging all of the cores we have on the machine. The question is, the only way we'd really be able to leverage all the cores is if we could rewrite this single-threaded Go program as a concurrent program. But remember, concurrency means out-of-order execution, and that means we have to be able to execute things out of order. So the question is this something we can do out of order? Does it matter what order we execute the files in as long as we execute all of them? And the answer is no, it doesn't matter. That's brilliant. That means we can leverage a concurrent algorithm if we want. And I want. So we're going to do that. But before we do that, there's some more information that I do want to gather, since this is our baseline. If I use the arrow tool and I double click in that blue area, it will bring up all of those blue areas kind of in a summation. And that's why what we see here now is the number of GCs. So the single-threaded Go program, right, the number of garbage collections that took place on this program was 445. I'm going to write that. We're going to see that in a second. And the only other, okay, get the average wall the average time it ran at GC, we got nanoseconds, microseconds there, right? So 242 microseconds is the average GC time here. But the wall clock's a good one. So the total amount of time in GC related to the wall clock is 108 milliseconds, okay? Which leaves me to one number that we need to calculate, which would be, let's say, the percent of time we're in GC based on that wall clock. So if I take that number, that 108, and I divide it by the 1669, that number, right, we get 6%. So 6% of the time right now, that GC, at least based on the wall clock, is kind of running. I like these numbers. Let's switch to the board for a second here. And so here's our single-threaded algorithm, right? It ran for 1669 milliseconds. We saw a 4-meg heap, pretty consistent, and also basically our max. 445 garbage collections took place. The average was 242 microseconds. It's really about all of them, not just one or two, but the wall clock is 108 milliseconds. So if we do the division here, it means that we were in GC for about 6% of the time. Now, one of the things here that we're going to start focusing on is making this a concurrent Go program, right? That's what we want to look at. We're single-threaded. I got 10 cores. I'm not using them for any application work. The garbage collector is using some of it. But let's see if we can turn this into a concurrent algorithm. Now, I'm all about we keep it simple until we can't. And I know the idea is to get to 1 million Go routines, but at this point, what I want to try is just using what I call this sort of fan-out pattern. One quick way to make something concurrent is just to throw Go routines at the problem. And Go is really good at handling Go routines. And yes, Go could handle 1 million Go routines. I don't know if I want 1 million Go routines necessarily all in a runnable state at the same time. But there are patterns and ways to create even millions of Go routines and kind of control their state. Now, at this point, we don't need to go to that level of complexity. Let's just throw a separate Go routine at each file. And when we do that, let the Go scheduler kind of handle all of that stuff. All right, so first thing I always like to do is define G is the number of Go routines we need, and luckily the built-in function length will give us the number of Go routines by just seeing how many files there are in the collection. Okay, the next thing now is this function can't return until all these Go routines are complete. We need a way to orchestrate that. What's nice is Go in the sync package has a wait group. Now the wait group is a synchronous counting semaphore. It's got an API of add, done, and wait. And at this point we need to add G, tells us how many Go routines we want to wait on. And then at the very bottom of the program we can use our wait group to say wait. So that will now be a blocking call while the wait group is anything other than 0. The moment that we can decrement that wait group back down to 0, this Go program, then that thread that's processing this can then return, okay, and report the number that was found. So we've got two parts of the wait group now. Now notice this on line 62, we have a loop. The loop is processing each file in that serial way, right? We were talking about this as a single-threaded Go program. So what we really want to do is I can take a literal function, put the keyword Go in front of it, and now what I'm going to be telling, I guess the compiler here, is that what I want is not for you to run this code in a single threaded, but I want you to create a new Go routine for every file that we're going to iterate over. In this case, 4,000 Go routines. Now you can see we've got some linter bugs here about closure. So what I'm going to do is make sure that we pass each document in, can do that. And that means that each Go routine will process its own document. If not, I'm going to be closing over the doc variable on line 62 and we'll be just processing the same file over and over again. Okay, now we still got to deal with decrementing. So once each Go routine finishes their 4 stages, what we need to do is make sure we call wait group done. This will decrement the wait group. And the defer statement is great for this because we can keep it at the top and it's guaranteed to execute as each go routine is terminating. So now I've just thrown 4,000 go routines at the problem. We might think now we're done. There it is, 4,000 go routines. We're waiting for them to all finish. But let me show you something here, some more Go tooling. Let's kill the tracer. What happens if I build this program now, but I instrument it with the race detector? It's going to be really important to make sure we don't have any data races before we run this. Okay, great. So I've done that. Let me just do a trace t.out and see what happens. Almost immediately, what happens here? A data race is found. The instrumentation has identified that we have at least 2 go routines trying to access the same memory location at the same time where one's performing a write. And if we look here, we kind of see it. Read at this address, previous write at this address. And we can see it's giving us the line numbers here, 96, 93, right? Now, if we come down here, 96 represents the go routine that we're running. Okay, you can see that the end of the declaration of the literal function. And then 93, well, that represents where the data race is found. And if you see here, we're using that local found variable, which wasn't a problem before, but is now, because all of these literal go routines are kind of closing over that. And this now is shared memory access that is unsafe. Okay, so how can we fix that problem now that we've found it thanks to the race detector? Now, what's super cool is Go has an atomic package, and we could use the add function here, but it's precision based, right? But for now, I can just say, fine. Instead of doing a plus plus, which is a read, modify, write operation directly on that shared memory, what I can ask the compiler here, right, I can say is, no, let's do this atomically. Now, we're having problems because found is just an int. It needs to be a int32 to match the precision. Now we have a problem on the return. I'll just convert it back. We're going to be okay. And now, by having an atomic instruction there, that should get rid of our data race, right? Let's see. We'll build it again. We run it again. And sure enough, no data race. It's running super slow because we've instrumented it, right, with that race detector. So the atomic instructions here now got rid of our data race. But, you know, there really isn't a lot of efficiency in using our atomic instruction there. We're going to have, right, 10 go routines running on 10 cores all at the same time, all feeding into the cache for that core, the 32-bit integer that is incrementing. In other words, what we're going to have here is some memory thrashing, because every time a go routine goes to increment found, it's got to invalidate the cache on all the other cores. So I don't know if there's much of a solution here for that, but we could do the following. What if I take the defer and I turn that into a literal function? Okay. What if I define maybe a variable called lfound? And now what I can say is this. What we'll do is each go routine will perform increments on a local variable, which means that that memory is on each go routine's stack. We don't need atomic instructions. We don't need anything. This memory is unique to each go routine. That's going to be really efficient, right? We love that. The problem is we do have to write it back to found at some point. That's a problem. But at least now we only have to do that 4,000 times as opposed to 28,000 times, at least for this given running program. So it's not super efficient, but it is still more efficient than leaving the atomic instruction down there in the loop. Okay, we have a concurrent version of our program now. Let's do the following. Let's build it. Let's run it again with our time. There it is. I'm going to run it twice. And you can see now we're running at a half a second. We went from basically 1.5 seconds to a half a second. We've shaved an entire second off this program by just leveraging this concurrency in this sort of fan-out pattern. It will be kind of fun to see, go tool trace, t.out, what this looks like now in our trace tool. Okay, so if we look at this, even just at this high level, we'll see that all 10 cores are now being used. We see a lot of density in the graph. We see that we're really leveraging the full CPU capacity of the machine. Pretty cool. We do see these sorts of spikes in go routine creation. There it is. There's a group here, there's a group there, there's a group there. These are go routines getting created, moving into their runnable state. I mean, I could select maybe at the peak here at 100 milliseconds, and we can see here we have 429 go routines in a runnable state. 10 are running at that point. This is good. I mean, we always should have about 10 running, but we can see these peaks of go routine creation. Look at the heat profile though. Not as consistent as we had before, right? There's a whole bunch of peaks. But what's really nice is we see a lot of density now at the core level. You see these go routines getting created, they're doing work, they're being swapped. So the machine is being used. Now, one thing I want to do is kind of explore the numbers that we care about, that we currently have on our board. So let's just take some measurements here. All right, so this measurement is essentially telling us that we actually ran this program. I want to just double check that we're right there on the edge. There it is, for 496 milliseconds. So I'll show you the board in a second, but right now this is going to be what I'm going to call our fan out. And this ran for 496 milliseconds. Brilliant. All right, what about our sort of memory usage here? It looks a little kind of all over the place. So I'm going to just kind of spot check some stuff here. And I can see here allocated is about 24 meg there. This one gets interesting. If we can get right in, I can open up 26 meg. So you know, we're looking at, I get some 24, I saw 26. So even that being a peak, right? We're looking at a Go program that's kind of at a peak, maintaining maybe about 20 plus meg of memory. And I saw about 26 there. So from my perspective, right, our memory right now, we need about 26 megs of memory to run this program. At least the GC is saying that's about as much memory it wants to allocate at any given time to keep this program running. Right? And you can see how with the creation of the go routines, right after there's a block of go routine creation, the heap kind of drives up, right? It's almost like a burst of activity suddenly, and now these go routines are moving into runnable states, and so we need a little bit more memory. So it's not surprising the correlation here of we create a bunch of go routines in here, right here. So we got 860 basically runnable, and now a bunch of memory is coming up. We have the same sort of peak, a bunch of more memory comes up. And so because we don't have this consistency with the go routines, we in this particular trace, we've got bursts of go routines getting created. We have some bursts of memory on the heap profile, but about 26 megs is kind of what we need to run this. Now, let's take a look and double click on one of these blue lines here, and we can get a little more information about garbage collection. So there were, in this case, only 149 garbage collections. We had 445 before. We have like 1.8, right, about 1 millisecond of average GC. And then the wall clock is 273 milliseconds. There it is right there. So if I switch over to the board right now so you can see that, and we just do a little bit of the math, 273 divided by that 496, we're looking at, from a wall clock perspective, being in the GC about 55% of the time. So half the time this program is running, it's in some sort of GC activity. Running at least, running 149 times with the average of 1 millisecond, with a full wall clock of that. But you might say, well, 50% of the time we're in some form of GC. Maybe that's not good. I don't know if that's necessarily not good, right? I mean, look at the time that we shaved. We went from 1600 milliseconds to 496. That, to me, is pretty good. Now, I did say to you that I wanted to be able to process 1 million files. And there's going to be a couple of problems here if we want to run 1 million files. Ideally, the big problem is, I don't know if it's going to be good to open up a million file handles, right? It potentially, the Go program could launch all these Go routines, and we could have hundreds of thousands of them at least running in some form or another, needing to open up file handles. And that number, maybe it's reasonable, maybe it's not. So from that alone, I kind of need a little bit more efficiency in how we're managing these Go routines, just on the file handle. Running 1 million Go routines in and of itself, I don't think is a problem. But now we're talking about operating system resources, and I'd rather not try to open that much at a time. I want to control it. Now, there's a couple of ways we can change this concurrent algorithm to deal with that. One way is to add what's called a semaphore channel, where we can create all these Go routines, but we, again, in an out of order execution sort of concurrent way, what we can do is say, look, based on the size of this channel, that will dictate how many Go routines can actually move into a runnable state. And that could be a fine solution. But I still will have to create and destroy like 1 million Go routines. And I think I could be a little bit more efficient if I use a pool. Now, we don't use pooling in Go really to gain better performance. Usually it's really about trying to have better resource management. That's what I'm going to be using it for here. What I'm going to do is create a pool of 10 Go routines and just allow those 10 Go routines to process everything that comes at it. All right? I think implementing that is a little simpler than implementing a semaphore channel where we still create all 4,000, but then we try to control what's in a runnable state. So let's get back to our code then. We could do that with a few changes here. So at this point, it's not the number of documents that will represent the number of Go routines. It's going to be asking the Go runtime how many logical processors, how many operating system threads are available for executing Go routines. That's what Go max procs provides. And if I pass 0, I'm not changing anything. I'm just asking for the number. And this number on my computer should be 10. So now we're just going to have 10 Go routines. Now, if that's the case, then ideally we're not ranging over the documents here, right? The idea is we only want to create that number of Go routines, G Go routines, 10. Now, if that's the situation, right, I don't have documents to pass into these 10 Go routines, not in the traditional way we were doing. So the question is, how do we get documents into this pool of 10 Go routines? This is where a channel can come in. So what we could do is create a buffered channel where we can pass string data, and we don't need more than G in the buffer, because what we can do is pass G number of documents in, 10, they'll get picked up right away, and we can stage the next 10 documents in there, getting ready to be processed. Now what that means here is inside of our Go routines, this pool, is what we'll do is we'll range over the channel, and we'll put our logic inside that range loop. Now what we've said is, fine, every go-routine blocks on this range. That's a blocking call to receive. And then as we send documents into process, one of the 10, we don't know, it's a concurrency, out of order execution. We'll pick it up, do the 4 things against that document, right? Open, read, unmarshal, range, search, and then come back to the top and wait for the next one. And we're basically limiting ourselves to, there'll be, depending on how quickly these files can be closed, we are managing our resources a little bit more cleanly here, because at any given time we know we'll have 10 files open, probably a few more, but we should be able to process 1 million documents this way. Now we're not done yet. We've got our go routines, we've got our receivers, so what we got to do next is start to feed that pool of go routines. And so we got to start sending these documents in. So down here we'll range over the documents and start feeding. Once the buffer is full, right, the first 10 get picked up, the next 10 are waiting for more go routines. We'll block there, but it's not a real inefficiency because nobody's available really yet to process anything. The key to this whole thing is closing the channel once we send the last document. That way this for loop can terminate once there's no more documents to process. What's nice is all the documents in the buffer will get flushed first, and then they'll start to receive that closed signal. These go routines will terminate, and then we'll have our answer. What's also nice about this is all of the counting, whether it's 4,000 or 1 million, we're counting against our local variable on the stack for each go routine. We only have to do this, in my case, 10 times, regardless of the number of docs. So we're also incredibly more efficient on the machine. This should run faster, don't you think? I think it should. So let's see what happens here, okay? So I'm going to build this new version. We're going to run it twice. And if you notice, we're actually not running faster. We're now running at about 1 second. We lost almost a half a second of time on this running program, while, as I'm telling you, we're more efficient. I'm controlling the number of go routines. There's only 10. We're controlling the number of files being open. We're more efficient on the hardware with the caching system. Why are we running slower? I don't know. Let's take a look at the trace. Okay. So let's take some measurements here. We're solid on our CPU processing. That's pretty dense. But let's double check the length of time it took to run this program. So sure enough, 882, I'm going to call this our pool program here, 882 milliseconds. So we're definitely slower. For sure we're slower. What about what's going on with maybe memory or something like that? I don't know. Let's kind of open this up a little bit. I'm looking for some peaks here. You can see there's no real consistency here. Even with the go routines are just there. Let's just open this up a little bit. And I'm sure if we can kind of select this peak, you could also see that the GCs, right? If you notice here, it's showing here that the next GC is starting at 30. We allocated about almost 30 here. So we're maintaining, it looks like, that's 1, 2, yeah, no. It looks like we're going to be maintaining about a 30 meg heap. If I kind of go through this and I click carefully, it looks like our heap is roughly the same as the last program. We had recorded about 26 megs. Now we're at 30 megs. So the GC is maintaining about a 30 meg heap, very similar to the last program. That's kind of cool. But I think this is going to be more interesting. Let's double click on the GC here. This program, even though it's maintaining that sort of 30 meg heap, right, is 858 garbage collections, 685 microseconds of average, but the wall is 587 milliseconds here. And if we do the math, then we'll see, let's see, 587 divided by 882, and we see that we're running at like 66% of our wall clock. So if I switch over here, these are our numbers, right? These are our numbers. I do want to double check the heap one more time. I just want to look at something here. I'm going to bring it in. I'm going to bring it over here. I'm going to open it back up here. I'm curious right in here. So there's our 4 meg heap, started the first GC. And what I'm seeing here is I click here, right? There's 5 meg, 4, 5, 5. If you really notice something that I think is more interesting, I'll bring this up. Really, the garbage collector is working pretty hard. That's 6, that's 4. If you really notice, and I may have clicked on some things that were kind of off, I don't think that this Go program is maintaining a 30 meg heap. I don't know where I got that number from. What we're really doing is maintaining a 5 to 6 meg heap, right? I don't know where I saw that 26. I think that was a mistake. I think really what's happening here is the Go program, we can continue to look at it. We made the Go program so efficient. We made it so efficient that it's kind of trying to maintain the same heap size as our single-threaded Go program. It's really, in this case, trying to maintain that 4, in this case we saw about 6, but this 4 meg heap. Why is it doing that? Why is it even able to? With only 10 Go routines, and with all the efficiency we added, the garbage collector is able to keep this sort of 4 meg heap. But what's happening because we're keeping essentially a 4 meg heap? You can see it in the trace. With the garbage collector trying to maintain the same size heap as our single-threaded Go program, we overpaced. The garbage collector is working incredibly hard here, trying to keep this really small heap size that it's capable of doing because of the added efficiency that we added to the Go program. Now, let's go back and look at this for a second. Our program ran at just under a half a second when we used this sort of 26 meg heap. We have a very efficient Go program now using a very small heap. So what's interesting here is Go has 2 knobs. They have a knob called the GC% knob, which lets you essentially set when the first and next GC should start. By default, that GC% number is set to 100. And what it means at 100 is start the first GC at 4 meg, and then the next GC should start when the memory doubles from whatever is left live in the heap. And that could allow the heap to grow, but the next GC then would be somewhat staggered, right? On our single-threaded, we saw that it was able to bring it down and maintain the 4 meg. On the fan-out, we saw that it starts at 4, but a lot of that is still left in the live heap, so the next GC starts a little larger, a little longer, and then it kind of finds its home. In this program, it started at 4, and then it was able to try to maintain that because of the efficiency. So one of the things we could do is we could set the GC percentage using a variable called GOGC and set it to maybe 1,000. Now if I set it to 1,000, what does that mean? What I'm going to say then is don't start the first garbage collection at 4, start it at 40, and then the next GC after that start 1,000% above the current live heap. We know that there's a real consistency in the use of memory here. And so I think if we use GOGC and start at 40 meg, it should be able to hold a 40 meg heap. And that means we should have less garbage collection, which means we should have hopefully less wall clock and less time in GC. So why don't we play with that number? Okay. So I can come back here, and this time when I run it, I'm going to say GOGC equals 1000. This means, again, start with a 40 meg heap, and the next GC will start 1000% above the live heap, but we know the profile of this program. And if you notice, we're now running faster. That was enough to, in this case, when we see the trace, we should see that we're no longer over-pacing on this program because we gave the program enough memory at this point, and it's still a small amount of memory. It's only, in this case, it should be that 40 meg. Let's come in here and try to click at the top there. And sure enough, you know, from where I clicked, you see 37. So we're maintaining now. This looks very much like our single-threaded Go program, except we're now maintaining a 40 meg heap all the way through. We're able to do that because of the way this particular program works. So if we look at this number again, 273 milliseconds, I'm going to write this stuff down here. So 273 milliseconds is now our new runtime. We know we're maintaining about that 40 meg heap, just like we were maintaining a 4 meg heap before. Let's take a look at our GC numbers. Let's take a look at our GC numbers here. There they are. And now what we see is we're not overpacing at all. If anything, we're down to just 27 garbage collections. That's brilliant because every time the garbage collection runs, there's going to be that latency. We've knocked it down to 27 by giving this Go program a 40 meg heap, essentially, right? We're at 786 microseconds of average, but more importantly, the wall duration is now down to 21 milliseconds. 21 milliseconds, and if we do the math on that now, that's really exciting, right? 21 divided by the 273, and we're back to now down to a 7%. 7% of the time we are now running in GC, all by turning that knob up and giving this Go program more memory because of how efficient it runs. Now this is Go 119, and one of the really cool new features of Go 119 is a new knob. This was really the only knob we had in Go, the GC percent knob with the environmental variable Go GC. And there's a runtime function that will let you set that too if you know that's how you always want to run that program. But there's a new variable now. It's called Go Mem Limit. And the Go Mem Limit now lets us set a memory limit for a Go program. In other words, we can ask the garbage collector, in a sense, this question. We know that when we run with a 40 meg heap, life is pretty good here, right? Maybe what I can do is tell the garbage collector this. Just give it a little bit more room. Say, hey, Go, garbage collector, look, I want you to cap my memory limit at 50 meg. In other words, try to keep this program running at a 50 meg heap. And then size the number of garbage collections and things we need within that memory, within this memory limit. In other words, the first garbage collection started at that memory limit and let it come down. And then try to maintain that over time. That's one of the cool things about what the memory limit can do. As opposed to using GOGC at 1000, which is fine, if I can maybe tell the garbage collector, look, I know what a good number is for the efficiency of this particular program. 50 meg is probably a good number. So if you just work within the bounds of the 50, which say, don't start the first garbage collection at 4 meg, start it at 50 and keep this, we're pretty good. Now you might think, well, Bill, isn't this setting just for when you're on devices with a low amount of memory? It could be for that, but because of the way programs sometimes work and burst and stuff, it's quite possible, depending on how your program's behaving, that the garbage collector still might need more than 50. And if you're on a real limited system where you're setting, let's say you're on a really limiting system or in a limiting container where there's only 50 and suddenly you get a burst of traffic, the GC is going to still try to deal with that. You still might get an out of memory error. So the Go team essentially always kind of says is, give yourself like 10% room on that anyway. So if you really are capped at 50 meg, lower that line at about 10%. But I've got a lot of memory on this machine. And what I really want to see at this point is, will the garbage collector respect, right? If I give it, let's say 50 meg here, or we can even try a 40 meg. Anyway, if I set this memory limit and tell the GC to work within that limit, will I get the same sort of efficiency? That's the question. So let's do the following here. Let's go back and run this program. But to use the new memory limit, you have to turn the GC, the GC percentage off. It doesn't matter anymore. It's not about that. What it's about now is how much memory we're going to work within the scope of. So let's just use 40 meg right now, which you label as, I need a capital B there, that. So now I'm going to tell the Go program, look, try to limit the amount of memory of this Go program to 40 meg. Keep within that scope. That's when you're going to kind of pace within the scope of that 40 meg. Now, if you look at that, we're still running a tiny bit slower at the 40 meg limit. Let me go to 50. Look at where we're at. We're basically on par with our Go GC 1000 when I tell the GC that we have a 50 meg limit. Let's go and look. I can't spell. Let's take a look at that trace. There it is. I mean, it looks really, really similar to what we had before, right? We see the big, long, straight green line. We're maintaining that sort of heap size. I can come in here and we can see that first GC, if you really look, it's interesting, right? The first GC is starting at around that 35 meg there. Okay, allocated 35 meg, boom. So even though I told it I have a 50 meg heap, right? It's able to kind of maintain it at 35, which gives me some room in case we have some burstable traffic. It's a really cool new thing in 119, and another way to kind of, if you know that you have a certain amount of memory that you only need, it allows the GC to kind of think about garbage collection and pacing in a different way. And so now here we're at 277. We're basically running the same with the Go mem limit at a 50 megabyte heap, 277. And if we look here, let me clear that. And if we look here, you see here we're at like 32 GCs just by using the other setting. One of the things I was playing with 119 as this came out, right? Let's run the 50 again. So that's like 290. What happens if we go to 60? It's really the same, right? There's that diminishing return. But at 40, tiny bit slower. And again, because if we saw on the trace, right? It didn't go all the way to that 50 line. It went in at about 35. So this is going to be going in probably a little bit smaller. We can look at it, go to trace, t.out. This is when we set the memory limit to 40. And if we can look at that first sort of GC that runs here, get in there, 25. So you kind of see it's trying to make sure that it has enough room to handle any sort of burst of traffic that might come in. And so in this case, with this particular program, all programs are going to be different, but using the 40 meg max boundary, we're running at about 25 meg heap. When I was using the 50 meg boundary, we're using about a 35 meg heap, and after that, the the numbers were point of diminishing return. So that's another way, when you know that you have an efficient program where I'd start with the GOGC, I'd look at, do we have a program that's going to be really consistent? We don't have burstable traffic anymore, right? We kind of did when we were just throwing a bunch of Go routines at the problem. So the GC burst, a little bit burst, we saw kind of a top limit. When we got really efficient with the pool, we had that really clean green line, right? We know when we're going to do the next GC, and instead of setting, I think, what's arbitrary, like GOGC 1000, now I can say, okay, look, work within the scope of a 50 meg heap and work within that, and we got that same consistency, and I kind of feel better setting a memory limit, to be honest with you, than some random sort of, in my head, random GOGC 1000, which for me is just like, okay, where do I start the first GC? That's how I was using that setting. Instead of 40, maintain it. But now it's more like, okay, here, just work within the scope of a 50 meg heap. So when we get to that sort of top line GC, get to the top line GC, and be consistent. But I hope what you've seen here with the tracing tool is we started with that single threaded Go program, which I always like to do. We identified that the real problem here was that we weren't using the full CPU capacity of the machine. So we went ahead and created that Fanout concurrent algorithm where we threw 4,000 Go routines at the problem. We saw we improved our performance, but we had to use more memory. In this case, we saw about 26 meg. And we were still running at about 55% in terms of the wall clock. Still really good performance, all good. We got very efficient with a pool because we wanted to process, say, 1 million files. We didn't want to worry about how many file handles we needed to open at any given time. So we went down to a 10 Go routine pool, and we noticed that we got slower because we overpaced. The tracing tool showed us that we were overpacing because the GC tried to maintain a really small heap. Well, we then went ahead and said, fine, don't start at a 4 meg heap, start at a 40 meg heap, hoping it can maintain it. It did, essentially, and we got better performance. Why? Because now we just told the guards, use more memory. It's okay, that's fine. We have the memory available. Use more memory, work within the scope. We got back down to about 7% of the time in GC, and I didn't write the numbers down for the Go memory limit because they were basically the same. I set the memory limit to 50 meg. It worked within a 35 meg heap, a little less memory than here. We got the same sort of numbers. I was able to control the amount of memory using Go memory limit as opposed to just setting that initial starting point for the first GC. Very cool stuff there in 119. And we improved the performance of our Go program starting at 1600 milliseconds all the way down to like 277 milliseconds. Big performance improvement there. And if we spent more time, maybe we can even be more efficient. But you can see how cool this Go tooling is in being able to inspect your Go program from a CPU perspective, from a memory perspective. We can make those code changes, we can look at it. And then you saw the 2 knobs that Go has for the GC and how we can use that to balance the amount of CPU time versus memory, right? CPU time versus memory. That's what it's all about. If you can give it more memory, we can reduce that CPU time. And there's a balance there, right? Always also a point of diminished return. But this tooling allows you to kind of do that study and then identify what's best for your running Go program. There's a great talk that was at GopherCon EU back in July by a member of the Go team that worked on the new Go mem limit. He provides sorts of guidelines on when to use that setting and when not. I definitely recommend that you watch that talk before you choose to use the new. In fact, you really don't want to touch these knobs unless you feel like you've done the work that I've done today here and you know that it's the right thing to do. And then you can hard code this stuff also using the runtime package in your Go program, so you don't have to worry about setting environmental variables. But that talk is out there in July. So hopefully you all learned something about how cool Go tooling is, how we can leverage this sort of tooling to help improve the performance of our Go programs. And if there's any questions you have after this talk, come and find me. And you can always find me on email, bill@ardan, A-R-D-A-N labs.com. You can find me on Twitter at goinggo.net. Don't hesitate to reach out. You're not bothering me. And I'd love for you to play with this stuff and learn more. So I'm Bill Kennedy, managing partner at Ardan Labs. Thank you for spending the time watching this talk.